Okay. This module is going to be about a new concept, which is this surface area calculation. So far in the course, we've been doing things with, contour integration, then we moved to double integration, for which we found areas, and then we just did pure double integrals in the context of Green's theorem, to do various things, right? Now, what we're doing is we're moving ahead towards surface integration and ultimately triple integration, which we need for the last theorems of vector calculus. And they're sort of the logical extensions of everything we've been doing so far. The first step towards surface integration, which is the sum of some function over a surface, is going to be a surface area integration, which is just finding the area of a surface. Okay? So it's pretty simple. It's a stepping stone to the more general surface integral and a surface flux integral, which is what we need for the rest of vector calculus. So as we go into this, let's remind ourselves something about 1D integration. So if we were doing, and let's think about something called arc length. So if we look at a function, okay, just as a function of x, okay, so we'll say y is a function of x, okay, and this thing has some variation, right? Some derivative as a function of x as we go. And let's say I want to know the total length of this curve. So if I was walking along it, what would be the total distance I traverse, okay, when I go from one point to another point in x. Now just looking at it, you can tell, if I'm going to go from this point to this point along x, if the curve is just straight, has no derivative, then it's just the distance along x. But the more curvy this thing is, the longer the arc length is going to be between these 2 points. And the more curvy means the more non-zero the derivative of y is. So the more non-zero it is, the larger the derivative, the larger the arc length integration is going to be. Okay? And if you actually think about this, really, if you just look at a little slope spot, let's just kind of blow that up. So the arc length contribution is this length here. I want to know the length, from here to here. So I'm just zooming that up. Okay. Well, so what is that? Okay. If you think of this as this is the step in x, okay, then this step here is the step in y, but that's just really the slope, right, times the horizontal step. Okay, that's the step dy. So dy equals the derivative of the function at this point here multiplied by the step size in the horizontal direction. Okay, so if I wanted to calculate ds, I'd say, okay, well, ds squared would be dx squared plus, well, let's say dy squared for now. Okay, and that is dx squared plus dy by dx squared. Okay, so this becomes 1 plus dy dx squared. So really our step contribution is the square root of 1 plus the derivative of our function multiplied by the step size. Okay, so if I want to know the total, I want to integrate this, the total path integral from one point to another, then that path, that arc length is going to be, okay, I'm going to integrate from x equals a to b, say that's a, and that's b, right? We're going to integrate that, and we're going to integrate ds. Okay, so that is the integral from a to b of 1 plus dy dx squared dx. This is what's important here. Okay? This is what converts, if you like, the step size in along the variable we're going to integrate and creates the contribution to the arc length as a function of that. And the important thing is that the more we have a non-zero derivative, the more curves we have as we go, the larger the arc length is going to be. Okay? Now, so that's fine. There's nothing super new about that. We've actually used this before. But what we want to talk about now is, okay, what if we're doing now, instead of doing a 1D integral, we're doing a 2D integral. So we have a surface, some sheet that's sitting over top of a region on the floor, right? So you have a big blanket, it's got some slope to it, it's hanging over top of the floor. And I want to know the surface area of this curve over top of the floor. Just like this, the curvier that surface is above the floor, the larger the surface area calculation is going to be. The smallest surface area you could have would be a flat, totally flat curve sitting over the floor. And what we find is that the integral does again depend on derivatives of the height function. So the function that describes the surface above the floor, the more non-zero its derivatives are with respect to the two variables over the floor, x and y. So the more non-zero the derivative of z, the height, over x and y is, the larger the surface area is going to be. And that in the note module we talk about this. So the area of that surface, I'll call it area surface, sure, okay, is, okay, we're integrating over some region on the floor for a minute, let's say. But now, very analogous to what we had that I just erased, we have a square root of a sum of two derivatives. There's two derivatives now because it's a double integral. Okay, so we have to consider ourselves with the function variation with respect to x squared plus the function variation with respect to y squared. Okay, and then we do that over the entire area. So we'll be integrating x and y, right? And we have to concern ourselves with this function f, which describes the surface over the floor, right? And if these two partials are zero, it just becomes equal to the region over the floor. That's the flat surface case. So this is the general equation we're going to use. Well, it's not general. It's specific to a height function defined over the xy plane. If we had a height function defined as y over the xz plane, then this would simply be surface area 1 plus partial of f, where f would be a function of x and z, partial with the x, partial with z. And then you'd integrate dx dz, because you have y as a height over that. This is described in the textbook in more detail. They go through these examples. Also in the note modules, we show these all. So let's do this. Let's look at just a straight up example, okay? And that'll end this recording, and then I'll do another example in a future recording, just so these don't get too long. Okay, so this would be an example problem. Okay, you would say, okay, so find the surface area. And by saying surface area, this is how we know we're doing a surface area calculation. Later on, we're going to say find the integral of a flux through a surface or something, and that's different. It's an extension of this concept. Right now, we're just doing area. So find the surface area of the portion of the sphere defined by x squared plus y squared plus z squared equals a squared. Yeah, that's a straight up sphere radius a, centered at the origin. Okay. So the surface area of the portion of the sphere described by this that is above the xy plane. So this is the positive hemisphere, top, and within the cylinder x squared plus y squared equals b squared, where we have, kind of obviously, b is less than a. So that would be what would be said in the problem. Okay. The first step in all these problems is understanding the region that we're trying to integrate, or the surface area we're trying to calculate. So you have to sketch it in some way. Okay. So for this one, let's just do that. So so this is z, this is x, this is y. Okay. So the first thing we're going to do is just try to draw this upper, okay, upper hemisphere, right? So this is the top half sphere, okay, right? And this is it coming out in this axis here. Okay. It crosses, so it's got radius a, so this is a this is A, and this is A, okay, the height A, right? And we're not considering the bottom because we're told it's above the xy plane, okay? So we have this curve, fine. If this was the question, we could do it by calculus. This is almost like deriving the area of a sphere. But we know the surface area of a sphere is 4 pi r squared. Okay, so the surface area of this upper hemisphere would be 2 pi r squared, where r would be A in this case. That's fine. That would be, we don't need calculus to do that. We already know that. But what we're being asked here is not just to find this, it's the area of this within the cylinder. So there's a cylinder, okay, of smaller radius, B. Okay, so this region here, so it's the top of the cylinder and the cap that would sit on top of the cylinder that's smaller than the sphere. Okay, so it's a portion of the upper hemisphere. So that's what we're trying to calculate. Okay, so the idea now is we're going to say, well, this is the height function above this region. So we're going to integrate over this xy region for x and y less than x squared plus y squared less than b squared. Okay, so inside this cylinder. And the function, the surface over that region is going to be defined up here as z squared equals a squared minus x squared minus y squared. So this is the surface that we're acquiring. This is the region A we're integrating over. Okay, so let's set this up. Now, will this remind us formally, just so remember, right? So what we're going to be after here. So this area, area of a surface, okay, is going to be this integral over. I've drawn it as A there, so I'll write capital A. Okay, this region here, and we're going to take. It's going to be 1 plus, and we're going to need down to z by x squared plus partial z by y squared. Okay, and then we're going to do this over dA. Okay. Now, before I wrote f, but this now we have z is this height function over this region. Okay, so that's what we're going to want. So what we got to do is build those. So let's see. So we're saying z, and we can think of that as the function of x and y. Okay, what is it? Well, z is equal to the square root of a squared minus x squared minus y squared. Right? Because this is the top of the sphere. The sphere is defined as x squared plus y squared plus z squared equals a squared. So solving that for z and taking the positive square root gives us the upper function. This is the function that defines the height over a. So this is the function whose derivatives we need to put into the integrand. So we've got to go ahead and just, it's not super trivial, so we'll just calculate those partial derivatives. So we need the partial of z with respect to x. Okay, so that would be 1/2 a squared minus x squared minus y squared minus 1/2, and then by chain rule, the interior derivative minus 2x. So we take the partial of this whole thing, that was to the 1/2, so 1/2 goes down, minus 1/2, and then we do times by the partial inside here, which is minus 2x. So that's what this looks like. So this looks like, let's say it's minus x over square root a squared minus x squared minus y squared. Okay. The partial of z with respect to y, okay, has a similar form. It's going to be 1/2 this minus 2y. So this will equal minus y by a squared minus x squared minus y squared. Okay. I hope you can see that. Right? You don't have to make that jump. You can just calculate the same way. Okay. I'm going to leave this diagram up here, so I'm going to work around it. Okay. So those are the two partials. Now what I got to do is just build this part. Okay. Do it slowly. Don't do it all in one shot and stuff it in the integral. Just calculate the partials, then build the square root, and then put it into the integral, decide on the limits of integration, and then finish it off. Don't do it all in one big shot. So if we build this, so if that's all true, then 1 plus partial z partial x squared partial z partial y squared. What does that equal? Okay, well that equals some of these guys, so it's 1 plus x squared over a squared minus x squared minus y squared. right? Because we've squared this now, right? And then we add, okay? And you can kind of see what's going to happen. There's going to be a simplification that we can make here. So these have the same denominator. Let's make that one the same and put them all together. So this becomes a squared minus x squared minus y squared, okay, plus x squared plus y squared divided by a squared minus x squared minus y squared. Okay. We've just made 1 equal a squared minus x squared minus y squared divided by that. Put them all together, and you can see what's happening. Cancel, 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 cancel. So this thing just becomes, we're in the bottom here. You see that? Yeah. So this is just a squared divided by a squared minus x squared minus y squared. Okay. That's what this interior sum of partials is. We're going to need the square root of that, and that's what we're going to integrate. So if we go back now, and go right back into here, so our surface area calculation is going to be that, so square root of that thing, I'll go kind of slowly here, right? And then dA. Now we haven't converted this to anything yet because formally we haven't decided whether we're doing this with Cartesian or polar coordinates. Seems pretty clear it's going to be polar coordinates, but we're not there yet. We haven't converted to r and theta yet. We will. And you see x squareds and y squareds is going to happen. Okay. So let's just simplify this for a sec. So that's, well, just right here. So that is, okay, still this integral, and then we have a out the top, and I'll write this as a squared minus x squared minus y squared minus 1/2 dA. Okay. Okay, so now's the point where we have to decide how we're going to handle this integration. If this were a week and a bit ago where we were doing double integration, we would start here. We would just give you this problem, right? Here we've used the surface area calculation discussion to show us how to assemble this integral and make meaning of it. But now we're just doing what we did a couple weeks ago in polar coordinates. Okay? So we are going to do this in polar. Okay? And I'm going to set, okay, so if I do this in polar, I'm integrating over this region A, right? So R is going to go from 0 to B, at this region capital A. So R is going to go from 0 to B, and theta is going to go from 0 to 2 pi, because our region we're integrating over is just a circle. Okay? And this will become R dr d theta. Okay? So this guy, if I put this over here, is going to be, I'll take the A out front, okay? From there, I'm going to go 0 to pi, I'm going to go 0 to B, right? And I'm going to go, now, what does this become? X squared plus y squared is r squared. So this is a squared minus r squared minus 1/2 r dr d theta. Okay. And now we're just doing an example integral right from the polar coordinate section. Okay. We've done this a lot of times. There's no dependence of theta in the integrand. There's no dependence on theta in the limits of integration for r. So theta can come out, and this just becomes 2 pi. So this becomes 2 pi times a times the integral 0 to b of a squared minus r squared minus 1/2 r dr. Okay, that's all we have to do now. Now, that's obviously a substitution. Okay. Let's do this real slow. So we're going to let u equal a squared minus r squared. So that means du dr is minus 2r. Okay, I have an r dr, so what I want, that means that r dr equals minus 1/2 du. Right? We do this a lot, and we do this really fast sometimes, but it's not worth it to try to do this too fast. Just go slow and steady as you work through this. I'm not going to change limits of integration. I'm going to put r back in later. So this integral, let's write this as capital, okay, a sub s. Okay, so I'll just go over here now. A sub s equals, okay, we still have 2 pi a and I still have 0 to b. Okay, r equals. I'll write r equal there just so I don't forget that that's set that way. And then I have u to the minus 1/2 and minus 1 over 2 du. Okay, that's how this is simplified. Okay, so that becomes this 2 pi a, and then we'll have, okay, so that will be u to the plus 1, so this becomes, I'll pick the minus 1/2 here, minus 1 over 2, it's from there, and then this becomes u to the plus 1/2 divided by that, right? And this is now evaluated at r equals b, r equals 0, right? So these guys cancel, but then we have a negative sign, so I'll write that as equals 2 pi a, and I'm going to have u to the 1/2. I'm going to put u back in, so I'm going to say a squared minus r squared to the 1/2, and then I'll affect this negative sign by switching these two. So this is going to be from 0 to b now. Okay, so we're almost done. Now let's do this right here. Okay, so this is 2 pi a. Okay, and then we have, what we got? Well, we'll just put, all right, so 0, so we have a squared, so that's a squared to the 1/2, so that says a, okay, minus, and then I have a squared minus b squared to the 1/2. Okay, that's that. That's almost, you could actually leave it there, but there's a natural thing to do here. So I'll just work on this form of this solution a little bit before we finish. So this AS, okay, would be, okay, I'll just write it again here. 2 pi a minus square root a squared minus b squared. Okay, that's a fine answer right there. But let's just do something a little funny. Okay, so this is 2 pi a squared. I'm going to write this as, I'll do the terms here. So 2 pi a squared, that's 1/2 4 pi a squared. That's what the first term is. Okay, minus 2 pi a squared minus b squared. Now, why would I do something? That doesn't look better than this. Okay, but I'm trying to make a point here. This is our final answer. Okay? But the reason I'm doing this is when you do things like a surface area calculation or a volume calculation or a straight up area calculation, you really want to at the end try to decide whether you think the problem makes sense or not, whether your answer makes sense. First thing always in these is the answer positive, right? So here I've got something minus something. We have to think about this for a sec. A is larger than B. We were told that in the problem, but that's the thing. The cylinder's within the hemisphere radius A. So this is positive, so it's not imaginary, okay? But these is a smallish number, so this thing is positive. You can actually see it up here. If A is bigger than B, then this thing is always less than A, so this thing is positive. First thing. Second thing, well, does it make any sense size-wise? So let's just think about A and B for a second. I wrote this way because 4 pi a squared is the surface area of the upper hemisphere entirely, without the cylinder inside. So if we let B get bigger and bigger and bigger till B was equal to A, so in other words, the cylinder got bigger, and then at a certain point, once B equals A, you're just integrating the upper hemisphere. So when B equals A, I better get the surface area of half a hemisphere back. So yeah, when B equals A, this goes to 0, this goes to 0, and I have the surface area of the top half. Good. What happens when B goes to 0? When B goes to 0, this thing better go to 0. Okay? When B goes to 0, then this becomes 2 pi a squared. This is 2 pi a squared, so this whole answer does go to 0. So this makes sense. It's positive for A larger than B. It equals the hemisphere case when B equals A, and it equals 0 as B goes to 0. All makes sense. Okay, that's a first example, pretty simple, but not trivial, of a surface area calculation where we end up using polar coordinates to execute the double integral. But the steps are surface area problem definition, then use the surface area formula, which is the square root of 1 plus the 2 partials squared, to convert the surface area into a double integration. And then we use the methods of double integration that we've been learning so far. Okay. We're going to do some more problems on this, and then we're going to extend the surface area calculation to a surface calculation in general, then a surface flux calculation, and then we're on to Stokes' theorem, which is the generalization of Green's theorem to 3 dimensions.